All right, we're back with another mechanics practice exam. This is my second attempt at making an exam this year. There was nothing wrong with the first one. It was a good content review, although some of the multiple choice were a bit too time consuming. So hopefully, with this exam, it's a bit more reasonable in the time frame. So it took me like an hour and a half to get through that first one, so I hope we'd get much under time for the multiple choice here. I'm never concerned about the FRQs though. All right, let's go. Two cars complete one revolution around the same circular track. Car A completes one lap in time t. Car B completes one lap in time 2t. Which the following compares the average velocity magnitude and average speed? Well, our relevant formulas here is that our average velocity is equal to the displacement over time, whereas the average speed is the distance traveled divided by time. So if we look at what's going on here, if you're going around a circle, you're not displacing anything. So your velocity is actually zero. So if you go around one lap of a track, your average velocity is zero. But your average speed wouldn't be zero. Your average speed is just the distance you travel, which is 2 pi r, divided by the time it takes. So looking there, the magnitude of the velocity is the same for both cars. And then for the average speed, car B takes longer to do it, so the average speed must be larger for car A. So pretty easy to start off here. We'll call that level 1 for sure. Next, we got the vertical position of an object is given by this sine function. Which of the following could represent the vertical acceleration? So there's two approaches here. First of all is the more like intended textbook approach, is we have the position function and we want the acceleration. So we know that acceleration is the derivative of velocity with respect to time, but velocity is the derivative of position. So we're really just taking a second derivative of the position function. So we just got to take two derivatives and see what we get. So for v, we're just taking the derivative of b sine ct. Just remembering to do the chain rule, although it doesn't really matter. We would get a regular cosine and then got to multiply by c for the chain rule. So we get b cosine of ct times c. And then for acceleration, we take the derivative of that function. And derivative of cosine is negative sine. And we get another factor of c. So you get negative bc squared cosine, sine of ct. So we're just looking for a sine curve that looks like negative sine. So if we kind of go through our graphs here, this represents sine, this represents cosine, this represents negative sine, and this represents negative cosine. So our answer choice is going to be C. And since there's two derivatives and you have to know what a trig function looks like, although we could just use Desmos, we'll call that level 2. That's pretty straightforward. You could also know that this is simple harmonic, and simple harmonic is defined as having an acceleration function that looks like the negative of its original. So you actually know you're getting negative sine from SHM. All right, a block of 3m is placed on the horizontal table. There's no friction. We place another block hanging. We want the tension in the string. So whenever we have these systems problems, the best approach is usually the systems approach or the big box method, where you put every part of your system in a box and only consider the external forces. Because this tension, although we are going to want it eventually, doesn't determine the acceleration of the system because it's internal. So if we look at the only forces that are unbalanced on this system coming from outside, we do have a weight of the 3m, but that gets countered by its normal force that's coming from the table. So the only unbalanced force on the system is the mg weight of the hanging block. So this allows us to use our fact that acceleration of a system is equal to F on the system divided by M total. And F net on this system would be mg. The total mass would be 4 m's because you have 3 m and 1. So our acceleration is g over 4. So now that we've done this, we can think about our actual free body diagrams now that we know what the acceleration is. So we can pick either of the blocks to use, but it's actually much easier to just use the 3m block because the 3m block has just its tension force getting pulled to the right, whereas the block M, the single M also has a tension up and its weight. So it's easier just to say that the F net on the 3M is equal to Ft. So we have 3M times A because F net equals MA is equal to Ft. So we get 3m times the acceleration of g over 4 is equal to Ft. So Ft would be 3/4 mg. You will get the same result if you use force balancing with the first block, because you would get m times g over 4 is equal to mg minus Ft, and you get the 3/4 once again. Just due to the number of lines and different connections, I gave this 3 stars, I believe. An object initially at rest has time-varying acceleration such that a is proportional to t. What functional dependence do we get for the power? So we have a couple expressions for power, and the one that seems relevant on this formula sheet is that power equals force times velocity, because we know about the acceleration. So since we know this acceleration, we know that F equals ma, so power will be equal to ma times the velocity. And we just got to figure out the dependencies there. So we see that A is proportional to T. So that means V is going to be proportional to the antiderivative of T. So this means V is proportional to T squared. Because if the derivative of velocity is acceleration, the derivative of what kind of function gets me a linear? Well, that must be a quadratic. So power must be proportional to acceleration times velocity. So we get a t, and we get a t squared, so we get a t cubed. So actually 2 hard ones back to back over here. I did deem this one hard as well. So there's other ways to do this. You could have also said that power would be the derivative or the time rate of change of kinetic energy, and kinetic energy is 1/2 mv squared. So you could see that v squared would be proportional to t squared squared, which would be t to the 4th, and a derivative of a 4th power is a 3rd power. So I thought this was also hard. All right, 2 blocks are stacked on top of each other. A rope is attached to the bottom block, and the system moves to the right at constant speed. The blocks do not slip relative to each other. The force of friction by the bottom block, on the top block by the bottom block has magnitude on top. The force of friction on the bottom block by the top block has on bottom, which of the following compares. So this should be very clear what's going on here, because this like word soup that's going on. Exerted on the top block by the bottom block. Exerted on the bottom block by the top block. This is clearly a Newton's third law pair. So what's going to happen is for the blocks to avoid slipping, there's going to be some sort of friction on the top block. And then there's also going to be some sort of friction on the bottom block at their mutual interacting point. And how do those forces compare? Well, anytime forces or objects interact, we know the forces are equal and opposite. This is just a Newton's third law pair. So the forces are equal because the mutual forces between 2 interacting objects always have equal magnitude, right? You can't break Newton's third law. I thought this was an easy one because it's just a statement of Newton's third law. I tried to make it really clear what was happening by using all of the words. That's usually your clue, and it's Newton's third law. All right, an object in uniform circular motion has centripetal acceleration A. if the radius of the circular path is r, how much time is required to complete one revolution? Well, we're talking about the time it takes to complete a revolution. We're also talking about circular motion. So when we're talking about circular motion, we know we can apply the fact that acceleration is v squared over r. And this is helpful because we are interested in the time it takes to go around the circle. So we probably want that speed. So v squared would be equal to a times r. So v is square root of ar. And now, the fact that it's in uniform circular motion means that we can just say the distance traveled is just equal to your speed times the time it takes. And we're interested in that time, t. So if we go around a circle, that would be a displacement, sorry, not displacement, but distance, 2 pi r. We said the velocity is square root of a times r, and we're solving for t. So this means t would be equal to 2 pi r divided by the square root of a times r. And if we look at what happens here, we see that one of the r's, this r, would be r to the 1, or r to the 2 halves, and we divide out r to the 1 half, so we're going to be left with 2 pi square root r over a. So there's really two ideas going on here, so I wrote this as 2 stars. You could have also deduced it once you knew there was a square root involved by saying that you knew that r should be on the numerator, because if you have a bigger circle, it should take longer. And same thing with your acceleration, which is sort of your like turning rate. So you could have figured out, once you knew it was a square root, which had to go on the numerator. All right, constant torque is applied to a disk which is not rotating at t equals 0. At t equals capital T, the angular speed of the wheel is omega, and the wheel has rotated through an angular displacement theta. What is the angular speed of the wheel and angular displacement of the wheel at 2t, so just twice the time later? Well, this is a kinematics question. And the fact that we know constant torque tells us that if tau is a constant, that means that we're going to experience constant angular acceleration. So we can just use some kinematics. Now, if you're experiencing constant acceleration, that means that your angular velocity is increasing at a constant rate. So if you gain a speed of omega in the first t, you must gain another omega in the second t. So we know we're going to be somewhere in here. And how do we know that? Well, we know we have the equation omega f equals omega 0 plus alpha t. So we see that omega is proportional to the acceleration and time. And then for theta, we have like our displacement kinematics that says delta theta is equal to 1/2 alpha t squared plus omega naught t. So even though the speed is increasing linearly, the angle is increasing quadratically. So we can see here that really our two facts that we sort of ended with was that omega was proportional to t, delta theta was proportional to t squared. So my time gets doubled. So omega is doubled and delta theta is quadrupled. 2 star. You had to understand constant acceleration and then do some kinematics manipulating. All right, a ball of mass 3 kilograms strikes the ground and bounces elastically with the ground, so it's going to have the same speed. And we want the magnitude of the impulse delivered to the ball by the floor. So if we look at actually the vectors as what's sort of happening here, is we see that we're moving down and to the right, and then we're moving up and to the right. And just to compute these things, our velocity was 5 meters per second, and elastic tells us there's no energy loss. So if we do that, this is just a 3, 4, 5 triangle. So these are our speeds. Because 5 cosine 37 is 4, and 5 sine 37 is 3. Okay, so now we can just calculate our impulse change, because the impulse, we just define the magnitude of the impulse as J, which is delta P, and that's just M delta V. So we have a 3 kilogram ball. And then what is delta V? Well, nothing ends up happening horizontally because I don't change my velocity horizontally. But what does happen is I change from -3 to +3. So I end with a velocity of 3 up. I started with a velocity of 3 down. So I just get 3 times 6, which is 18 earthers. So that makes that B. That's a pretty standard impulse question. All right, 2 scenarios in which we have a block of mass m on a ramp. We just change the ramp angle, and we're interested in comparing the gravitational force and the normal force on the block in each of these cases. Well, first of all, it's the same block. So we know if we draw a free body, because we're talking about forces, we have the same mg that's pulling on the block in each of these cases. So we do have the same gravitational force. But then if we think about what's happening with the normal force, is the normal force pushes directly out of the surface in each of these cases. And what the normal force does is the normal force balances the into the ramp component of the gravitational force. So sometimes, instead of drawing just the full mg, which we needed to know for the magnitude, we like to split it up into its down the ramp component and into the ramp component. So we know that going down the ramp is mg sine, and going into the ramp is mg cosine. So what that means is that the normal force balances mg cosine, and since there is more of the mg into the ramp when it's flat, there's going to be a larger normal force when the ramp is flat. And why is that? Well, it's because the normal force must balance mg cosine theta. Also think about the extremes. You get the full mg if you have no ramp angle, right, if theta is 0, and you get no mg if you have a completely vertical ramp. Thought this was level 1. All right, now we're on to some spherical asteroids that are spaced along the x-axis. And we're interested in first finding where their net gravitational field strengths cancel. So where could you place an object such that it would not get pulled towards either sphere? So this is a semi-quantitative one. We don't need the exact point, but we're interested in what region it could be. So we're really just saying where the net gravitational force due to both spheres is equal to 0. But we also have this concept of the gravitational field, which is equal to gm divided by r squared. So it's an inverse square law, just like Newton's law for gravity. So let's try to figure that out for both of these spheres. So we'll start with the base case of the just mass m. So we'll say at a quarter d, it'll have a field strength of 1. 1 on the top and 1 squared on bottom. Then we double the distance, so instead of a 1 on the denominator, it's 1 squared. So that would make a quarter. Then instead of a 2 squared on the denominator, we'd get 3 squared, which is a ninth. So that's what's going on with the smaller sphere. And then for the larger sphere, well, it has 4 times the mass. So all of its values, it's not going to go 1, 1/4, 9. I just multiply each of these by 4. So this would have a field strength of 4 at the first tick mark. It would have a field strength of 1 at the second tick mark. And it would have a field strength of 4/9 at the second one. So what we can see is happening here is that the net field, well, clearly, if we're close to this asteroid, 4 1/9, clearly 4 wins at this tick mark. The purple wins at that tick mark. The purple also wins at this tick mark. But the purple loses at this tick mark. So we see that there is a field direction change between 1/4 and 1/2. So that is our point of 0 net field. thought that was level 2. And then suppose we release the spheres from rest, which of the following points could represent the location at which the spheres collide? So this involves understanding that the two-sphere system is isolated. And if a system is isolated, its center of mass cannot move. So what this means is that the center of mass must be in the same spot. So if you release two things from rest and they're allowed to attract each other, they will collide at their center of mass. So we can just find the center of mass. So we have a 1m mass located at 0, and we have a 4m mass located at D, and our total system mass would be 4m plus 1m. So we just get 4md divided by 5m, which would be 4/5 times d. So if we look at what region contains that, well, it's going to be this point D right here, because 3/4 is 0.75 and 4/5 is 0.8. So it's just slightly beyond this tick mark. I also thought this was level 2 because you had to know the center of mass thing and you had to do a bit of deriving. A thin rod has mass 12 kilograms, uniformly distributed. The rod is pivoted about its left end and initially held at rest. We let it go, and the rod rotates. We give you the rotational inertia of the rod about the pivot, and we want the acceleration magnitude, angular. So this is a torque problem. So we know that the key here is that angular acceleration is just net torque divided by rotational inertia. And that was given to us. Our rotational inertia, we had to make sure it was the right one, was about the pivot. And what is our torque? Well, if you have a uniform object, we know that its gravitational force can just be collapsed sort of to its center. And we actually know what that is because the mass is 12 kilograms, so the weight, mg, is 120 newtons. So this allows us to just say that the torque about this pivot point right here would just be r times f, because everything is nice and perpendicular. So half of a meter is just 0.5, and the force is 120, so the torque is 60 Newton meters. So our torque was 60, and our rotational inertia was 4, so we get 15 radians per second per second. Multi-step, you had to combine torque and Newton's second law, so we'll say that is level 2. All right, our union-mandated relative velocity question. So here's our situation. We got a person on a skateboard moving at 5 meters per second relative to the ground, and then they throw a ball at 3 meters per second relative to the skateboard. And we want to find the horizontal speed that this observer measures and the acceleration this person measures. So what's happening is person A throws the ball at 3 meters per second backwards relative to them. So this means that person B, they are going to see the ball sort of had a velocity of 5 meters per second, but it's getting sent 3 meters per second in the opposite direction. So it's not going to approach them as quickly. The person couldn't totally cancel the skateboard velocity, so they're going to measure 2 meters per second. And all observers can disagree on speed, but they don't disagree on acceleration. So everyone agrees the acceleration is going to be g, because everybody agrees on accelerations, but people can disagree on velocities. A certain force has a potential energy function that varies on the x-axis. We have the energy function, and we want the force exerted on an object placed at x equals x naught for a positive value of x naught. So we have this relationship that says the force exerted on an object in the x direction would be the negative of the slope of the potential energy. Because again, forces are trying to push you downhill to lower potential energies. So we just take a derivative so we just get negative 3ax squared. And we're given that this x0 is a positive number. So we are going to be just given this sort of negative 3a x0 squared. X0 squared is always positive, so our force would be in the negative x direction because this negative just remains. This was just a plug and chug, I think. All right, this is a real tricky one. We got our shell theorem, which is always a challenge. Spherical planet of mass m, radius r, has a non-uniform mass density, which is given by this ugly-looking function. We want the field strength at r equals big R over 2. So we're going to be finding the field strength from a planet with this strange mass distribution. Now, there's a shortcut if you know some Gauss's law, but the shell theorem says that the gravitational field strength at any point is g times the mass that you're enclosing divided by the distance you're at squared. So we just need to find the enclosed mass because we know that the distance we're at is going to be r divided by 2. So to find enclosed mass, we have to do some calculus with this function. So again, we have this sort of spherical planet, and we're interested in the field strength at r over 2. So we need to find sort of how much mass m is in that distribution. So the enclosed mass can be found by integrating density with respect to volume. So that's the trick here, is that it is a volume density. So how can I build a sphere? Well, I can build a sphere by taking my density function and multiplying by these tiny spherical shells. So this is the relevant substitution, which makes this one of the hardest problems on the whole test, is seeing that you have to break up this planet into spherical shells. So we know we're going from 0 to r over 2. Our density function is 5m over 4 pi big R to the 5th times r squared times another r squared dr. So we'd end up getting, on my 4 pi cancels after I multiply by that extra 4 pi. So we get 5m over big R to the 5th times the integral from 0 to r over 2 of r to the 4th dr, which would be 5m over big R to the 5th times r over 2 to the 5th power divided by 5. So we see that all the r's cancel. All the r's cancel, and I would have a 32 in the denominator. So this is actually m divided by 32. So we do actually get something nice looking out of this. And then we can go in and plug in where our enclosed mass was m divided by 32. So we get gm divided by 32 times 1/4 r squared, and 32 divided by 4 is 8. So we get gm over 8 r squared. Wow. That is absolutely going to be our most time-consuming and tricky one today. All right, now we got 3 rods of the same length. They have the same uniform mass density. We bend them into this U shape, and we're interested in their center of mass, the y coordinate at least, because the x coordinate is just going to be somewhere along this, this midline. So since we have uniform density everywhere, we can just shrink this. We can just shrink this system into a 3-particle system where we could shrink down the bottom rod to just a point at 0, 0. We could shrink the right rod and left rod each to points that would be at some x coordinate that we don't care about, and then 15 centimeters. So now we can just find the center of mass using our formula. So our y center of mass would be, we have one of our m's is located at 15, one of our m's is located at 15, one of our m's is located at 0, and we have 3 of them. So we end up getting 30m divided by 3m, which would be 10 centimeters. I definitely say this is going to be a level 2. Fix my thing here. This would be a level 2. You could have kind of seen where the answer should be. The 10 makes sense because you know that it's going to be just slightly less than 15 because both of the vertical rods want to drag the center of mass towards 15, but we're going to be a little bit beneath it because one of the rods is at 0. So we're twice as close to 15 as we are to 0. And I said this was a medium. All right, spherical star has mass m and is initially rotating about its center with angular speed v naught, or omega naught. Then the star collapses, forming a smaller sphere of the same mass, and it rotates at an angular speed omega final. We want to compare the two omegas with justification. So this is really just our figure skater. Because whenever we have this sort of radius change, we should be thinking of angular momentum. So we have L0 equals L final, and angular momentum is I omega. So if this is our constant, if our initial state is constant, we just need to figure out what happens to the moment of inertia. Well, we know that the moment of inertia is going to be proportional to radius squared in some way, because I is mr squared with some constant in front, depending on the shape. So if you bring your mass closer to your rotation center, that is going to decrease your rotational inertia, right? Because as r decreases, I also decreases. But you can't just decrease for free, right? We have to maintain that same angular momentum. So if we shrink the moment of inertia, we must grow the angular velocity by the same amount in order to create no net change in angular momentum. So that means our omega final is greater, and we used rotational inertia for that. I thought this was pretty straightforward. It's really the figure skater problem. All right, now we got a collision where we have a block of mass m moving at speed v0 towards another mass m, and we're considering what happens to the speed v0 under each of these conditions. So first, we could stick together after the collision, and second, we could say the incoming block bounces elastically off the stationary block and stops. So we're saying that in the second case, we're actually stopping after the collision. And we want to rank the 3 given speeds. So we have the incoming speed v0, we have the stick together speed v1, and then we have the outgoing speed v2 after the bounce and stop. Okay, so first of all, in scenario 1, both of these blocks have to share the momentum. So if both of these blocks are contributing to the momentum of the system, we're essentially doubling our mass. So this velocity is going to be v0 over 2. Because you have twice the mass and need to create the same momentum, you have to half the speed. Now for our second scenario, we have stopped one of the blocks. So if the momentum of the first block is 0, and we still have to create the same original momentum, v2 must actually also be the original speed v0. Because we're essentially just swapping which block has the momentum. So that's one way to create an elastic collision, is just transfer all of your momentum from one block to the other in this equal mass case. So we see that it will be answer choice B. And I thought there was enough reasoning here that made this hard, because you had to identify the equality here, and you had to be able to do the inelastic math. All right, now we got a mass spring system A block of mass m is attached to a spring. We displace the block a small distance before releasing it from rest. We want the energy stored in the spring as a function of time. Well, we know what the energy is stored in a spring. The energy stored in a spring is 1/2 times k times delta x squared, where delta x is your extension. So all we need to do is find what our extension is as a function of time. And this is simple harmonic motion, so we know there's going to be a sinusoid involved, as shown by the answer choices, which I totally didn't mess up the first time and forget a square. But we know that simple harmonic motion follows sine or cosine, and here we're releasing it from rest at t equals 0, so we're maximizing our displacement, so we want a cosine function. Because you get no displacement at 0 if you used sine. And we also know that for a mass spring oscillator from our formula sheet, omega is the square root of k over m. So we can just combine these results. And we can see we get answer choice C. And notice a lot of these just involve the simple flipping of the frequency or using the wrong trig function. All right, an object is placed at the origin at the xy plane at t equals 0. The object is released from rest and then experiences a uniform acceleration given by 3 hat minus 4 j hat meters per second squared. How far away is the object after 4 seconds? So because we're starting from rest, we don't need to do a whole bunch of Pythagorean theorem, although it will still work. What we can do is just see that my total acceleration is just going to be the acceleration in the x direction squared plus the acceleration in the y direction squared, all under square root. And no surprise here, if our acceleration components are 3 and 4, our acceleration magnitude is 5 meters per second squared. How far away are we after 4 seconds? Well, we have a uniform acceleration, and we have the time, so we can just do... I'm trying to... Do I want it delta x? Yeah, I'll just do it delta. No, we'll do r. Our displacement would just be equal to 1/2 times a times t squared plus an initial velocity term that's not there. So 1/2 times the acceleration, which was 5, times t squared, so 4 squared. So we get 4 squared is 16, half of 16 is 8, 8 times 5, 40 meters. Now, you can get the right answer if you do this kinematics twice in each component, then do the Pythagorean theorem. It will still work out for you. I thought this was a level 2, just like the previous one. All right, now I got some mass spring systems to compare. We're hanging a mass from 1 spring or 2 springs in series. We're going to be interested in comparing their spring constants and their oscillation frequencies. So it's pretty clear that the first spring constant is k, but for the second one, we have a rule that says in series, since these springs have to experience the same force due to Newton's third law, k in series adds like parallel resistors or like ordinary capacitors in series, where they add via the reciprocal rule. So essentially, this is just having my effective spring constant because I get 2 over k to the -1. So that's k over 2. So what this tells me is this spring constant is effectively k over 2. So system 1 has the greater spring constant. And then what's going to go on with oscillation frequency? Well, we know that k directly affects the period of oscillation. And the frequency is the inverse of the period, because the period is how many seconds it takes per cycle. 1 over that would not be seconds per cycle, but cycles per second, which is frequency. So frequency is defined as the reciprocal of period. So we get this result. So this tells us that the results are going to be the same. The thing with the larger spring constant will also have the greater frequency, because that should just make sense conceptually, because the spring constant is telling you sort of how strong your restoring force is. So it makes sense that if system 1 is a larger spring constant, it's getting pulled harder by that restoring force, so it's going up and down at a faster rate. Level 2. This is borderline level 3 because of the series rule if you don't know it. 3 blocks are connected by a series of ropes. A 12 Newton force is applied and the blocks are pulled across a frictionless surface. The blocks start from rest. We want to calculate their speed after traveling 9 meters. Well, I got a whole bunch of extra stuff happening in the middle here, but I don't care about that. This is a system of objects, so I'm totally just going to put everything in a box. So we'll do the same thing we did with the Atwood, where we can say that the acceleration of the system is the net force on the system coming from outside divided by the total mass. So I have a 12 Newton force, and I have a 3 plus 2 plus 1 kilogram object when I put all the masses in the box together. So I'd get 12 over 6, which is 2 meters per second squared, which is not A. That's the acceleration. Answer, we're asking about the speed. So now we got to do some kinematics. So I have their acceleration. The thing that's missing is time, and I'm also not interested in time. So if you're looking for the kinematics, that does not include t. It is vf squared equals vo squared plus 2ad. So this means our final speed will be the square root of 0 squared plus 2 times 9, which would be the square root of 36, which is 6 meters per second. Level 2 once again, because you have to synthesize a bit. All right, a ladder is leaning against the wall, making an angle theta with the floor. There is friction between the ladder and the ground, but there's no friction between the ladder and the wall. Determine the minimum coefficient of friction between the ladder and the ground such that the ladder does not slip. Well, we should start with forces. So, of course, we're going to have a gravitational force, mg, at the center of the ladder. There is friction between the ladder and the ground. So we know there's going to be 2 forces from the surface. There's a normal force going up, and there's a static friction force to the right. Because if we think about what's going to happen, if we allow this to slip, the end of the ladder is going to move to the left. So to prevent slipping, we're going to get rightward friction. And also, since we are in contact with the wall, we are going to get a normal force from the wall, but nothing else because there's no friction. Because friction is the name for the surface force along the surface. All right, so now we can set up some force balancing. So we know that the only vertical forces are the normal from the ground and the mg, weight. So we know that normal force and mg have to balance. Then also we know horizontally, the friction force and the wall force have to balance. And why that's helpful is because if we want the minimum coefficient of friction, this must mean we're maximizing our static friction force. So we also know that the maximum value of static friction is mu times the normal force. And the normal force is just mg. So if we can figure out what this force is from the wall, we're essentially done. Well, we need another equation, and that's where torque comes into this. So we can sum up the torques about the bottom and set it equal to 0. That just eliminates the friction force I know nothing about. So if we look at what's going to happen here, we're going to use lever arm for these torques. So mg is vertical. So we want the horizontal distance to mg, which would be L over 2 cosine theta. And then that torque must be balanced by the wall. And since the wall force is horizontal, we want the vertical distance to the wall from the bottom. So that would be the full L times sine theta. So just equating these things here, we get F wall would be equal to mg over 2 times cosine theta over sine theta, which is 1/2 mg cotangent theta. So now we can just equate our forces, and we can say that mu times mg is equal to 1/2 mg cotangent theta. Goodbye mg. So we get mu is equal to 1/2 cotangent theta. This is also up there for the most time-consuming one on the test. Absolutely 3 stars. All right, consider the following 3 locations near a spherical planet of radius r. A lot of gravitational field strength today. Location X is at the center of the planet. Location Y is at the surface of the planet. Location Z is an altitude r above the surface of the planet. So we have this sort of picture where our points are X, Y, and Z. And we just want to rank the field strength G at each location. Well, our expression for G, as we used with the shell example, was big G times the enclosed mass divided by distance from the center squared. So at position X, I'm at the center of the planet, so I'm enclosing no mass. So G is equal to 0 at the center. Then at position Y, I'm enclosing the entire planet's mass, and I'm just 1 radius away. And then if I'm at position Z, I'm still enclosing the entire planet, but now I'm getting farther away. So I have a larger denominator on that term there. So this means we have no gravitational field at the center and maximum field strength at the surface. And if you know anything about the graph, you could have gotten this done in like one line if you just know what the gravitational field strength looks like for a planet, where it's linear inside and then it's inverse square outside. And you actually know it's maximized at the surface. You could have figured that out as well. I actually did think this was 1 star, but I feel like this should be bumped too. All right, now we have a hoop and disc that are serving as these sort of physical pendulums, where we pivot them along their top and we give them a small displacement and look at the period. We want to compare their oscillation period with valid justification. So if we look at our formula sheet, our expression for the period of a physical pendulum is 2 pi square root of I, about the pivot point, divided by mgd from the pivot. And this should make sense because period should be increased if you have more inertia, where it's harder to change your motion. And this mgd is really the restoring force or the restoring torque. So this is sort of a fact that we should be pretty well aware of, that if the moment of inertia is sort of the squared distance segments with respect to mass, moment of inertia is high if your mass is spread out far from the center. So it should just be a fact that we know that I hoop must be larger than I disc. And if you know the numbers, you actually know it's mr squared for a hoop and 1/2 mr squared for a disc. Not that that matters. But we do know that I hoop is bigger than I disc. And since that happens, we know that the object with the larger rotational inertia must have the larger period because all other factors are equal. So it's the hoop for reasoning B. Because A is actually false, because the torque, mgd, is the same on both objects. All right, an object experiences a time-dependent force given by this function. Consider the following 2 scenarios, where we exert the force over an interval capital T or capital 3T, and we want the impulse magnitude ratio. So how do we relate impulse to force time functions? Well, we know that J is the integral of the force function with respect to time. So we can just integrate to an arbitrary time so we can see the dependence. So our force function was AT squared, which means that we get 1/3 times A times T cubed is our impulse delivered. So what does that tell us? Well, that tells us that J is proportional to T cubed in this problem. So if we know that J is proportional to T cubed, and that is the only difference between the two scenarios, is tripling the time for one of them, this means that J2 would be equal to tripling the time, then cubing it for that dependence. So we get J2 is equal to 3 cubed, which is 27 times J1. This is a high level 2. I would say this is borderline level 3. You know, let's say this is level 3. All right. A ball is launched from the ground at an angle of 53 degrees above the horizontal. The vertical position y of the ball above the ground is shown as a function of t. So we do know that we have this sort of vertical velocity 53 degrees. We want the horizontal range of the ball. So this is a projectile problem, and we know that range, that's the just horizontal. There's nothing interesting happening horizontally. So we can just say that the distance traveled in the x direction is just your speed in the x direction times time. And we see that we're in the air for 4 seconds. So the objective of this problem becomes, can we find Vx? Well, what other information do we have? Well, there's a variety of things you could do to find the initial y velocity from this. You could use energy, you could use kinematics. I think kinematics is more of my intended approach. So we can see that Vy equals 0 after 2 seconds. So we could say that Vy equals Vy0 plus At. After 2 seconds, I have 0 y velocity. After accelerating at negative 10 meters per second for 2 seconds. So my y velocity was 20 meters per second. Now that's not the speed I'm going to put in this expression for range, because that is the x velocity. So what I have to do is just a little bit of trigonometry. So now we found the y velocity was 20 meters per second. So we could just set up some sort of relationship. And technically you'd want to use tan here. Tan 53 degrees is equal to 20 over Vx. And if you did that, I'll move this up a bit. We would see that Vx is equal to 20 divided by tan 53 degrees. Typing that into our calculator, tan 53 is going to be 4/3. So that makes 15 meters per second. It's also a 3-4-5 triangle. You could have done it that way. So this is 15 meters per second for 4 seconds, which is 60 meters. This was also 3-star because of the trigonometry step. All right, 2 masses are attached by strings to the concentric pulleys shown below. Determine the magnitude of the rate dl dt at which the angular momentum of the 2 pulley system is changing about its center once the blocks are released from rest. Well, we have this sort of pulley here, and we know each of these masses are going to be pulling down with their individual weights. So we have an mg at the inner pulley, and we have a 3 mg acting on the outer pulley. So this is interesting, the rate dl dt. Well, we have this relationship that says the only way to change your angular momentum is to exert a torque on the system. So all we're doing is finding the net torque on the system. So what is the net torque on this system? Well, driving the pulley counterclockwise would be a 3 mg acting on a distance 2r from the center. And then trying to pull it the other way, clockwise, would be an mg oriented 1r away. So we get 6 mgr minus 1 mgr, which makes 5 mgr. Couple steps, level 2. A block of mass m is suspended from rest by 2 identical cables, each oriented an angle theta above the horizontal. Which of the following statements is correct about the tension? So we have to decide if the tension in each cable is mg over 2, exactly half the weight, or mg over 2 sine theta. Well, if we look at our force balancing here, by symmetry, we see that the tension sort of does two things. Where the tension is going to pull us horizontally, equally in both directions, canceling, and then we have our vertical tension. So what we see here is that with this system, since we're talking about the vertical balancing here, we see that this work, or this force that's caused by the horizontal tension component, it's essentially doing nothing. So because that horizontal tension force is being wasted, only the vertical part is actually serving to balance. So we see that 2 copies of ft sine theta must balance the gravitational force. So ft would be mg over 2 sine theta. And that's answer choice D. I did deem this 1 star because I thought the justification would kind of give it away. And once you saw it was a component problem, that kind of narrowed it down, and you could see that it's really the vertical components that are doing stuff. All right, a bucket of mass m is attached to a string of length L. The bucket is swung in a vertical circle at constant speed v. What is the tension in the string when the bucket is at the top of its trajectory? And we have all these options. Well, at the top of its trajectory, we're going to have something like this. So we know that the weight of the bucket, mg, is going to pull down, and we also know that the tension in the string connecting us to the center of the circle is also straight down. So what this tells us is the net force at the top of the circle is the sum of mg and the tension force. Well, since we're moving in a circle, we know that the net force is supplying a centripetal force, so we can say that is equal to mv squared over r. And then just solving and understanding that the radius of this circle is just going to be the length of the bucket string, L, we can say that ft is equal to mg minus mv squared over r. Or sorry, mv squared over r minus mg. And it should make sense that the tension doesn't have to be as large now because mg is sort of helping us in our quest to go around the circle. So tension is actually maximized at the bottom of the circle because the tension has to get you going in a circle and fight gravity at the same time. So answer choice B is the tension at the bottom. All right, thin rod, length L is placed along the x-axis. The little rod has linear mass density. We're given a lambda function. We want the moment of inertia of the rod about its left end. Well, our expression for moment of inertia is I is equal to the integral of r squared dm. And lambda is defined as dm dx. It's your mass per unit length. So we can always substitute dm is equal to lambda times dx. This is like our 1D version of that volume substitution we did with the gravity in the planet. So our r coordinate is just going to be x, and our lambda function was ax dx. That's our substitution because we said that dm can just be written as lambda dx. And the rod length is L. So the a comes out of the integral, and we just get AL to the 4th over 4. I don't know why my colors are messing up right now. Because you had to know that you had to add that square factor in, we're going to give that a 2 star. It's not just a basic integral, you had to substitute the lambda in. All right, a falling object experiences an upwards drag force that's linearly related to its velocity, and we want to write a diffeq to get the speed of the object. Well, if we have a diffeq with forces, we want to use the fact that F net is equal to mass times acceleration. So what is the net force on our object? Well, we know we're falling, so we're going to have this gravitational force mg, but also opposing the falling would be a drag force, Fd, which we said is equal to Cv. So our net force would be the forces helping our motion, mg, minus the forces opposing our motion, Cv, and that's equal to m times a. And acceleration is the derivative of velocity, so we can say mg minus Cv is equal to m dv dt. I'll be consistent with my capitalization here. Let's make these lowercase to match the problem. So we want to solve for dv dt, although we can tell what the answer is going to be just by looking at them. We can divide through by m to get dv dt is mg over m, which is g, minus c over m times v. And if we solve this, you'll get some sort of decaying exponential. It decays to like a maximum speed, so it's that exponential approach function that looks like this. Because as you get faster, the drag force opposes you more. All right, we have a potential energy function here. So an object with mass 2 kilograms has a mechanical energy of 20 joules when at x equals 0, and we're interested in finding its speed upon reaching x equals 1. So this allows us to just use energy conservation, because we know that the total energy of this system is 20 joules. So we also know that at any time we can set the sum of kinetic and potential to be equal to 20 joules. And we're going to do that at x equals 1, because we can just read the graph to say that when x is equal to 1, the potential energy is -4. So the kinetic energy at x equals 1 is 20 plus 4, which is 24 joules. So now we just want to find the speed of the 2 kilogram object at that time. So we just know that kinetic energy is 1/2 mv squared. So we're just solving 24 is equal to 1/2 times 2 times v squared. The 1/2 and the 2 cancel, so we just get v is the square root of 24, which is just a little bit less than 5, so we can see it's going to match the 4.9 answer. Now, if somehow you got negative total energy, we could find a situation where if your kinetic energy ended up being some negative value, that would mean you couldn't reach that point. All right, now we have some torque comparisons here, where we have a square that's pivoted about its top left corner, and we want to rank the torques exerted by each of these 3 forces about this pivot point. So we know that torque is equal to R perpendicular times F. So we're going to use the lever arm approach on this today. So this means you can take the full force and just multiply by the perpendicular distance from the pivot point to the line of action of that force. So for example, for F1, the force has a magnitude of 1. Nope, the force has a magnitude of 2. And what is the perpendicular distance? Well, the force is vertical. So what's the perpendicular distance? The perpendicular distance is 1. So the lever arm is 1 there, so I get an effective torque of 2. Now for the second torque, I have a force of 0, or I have a force of 2. And my lever arm, well, my force is vertical. So I'm asking myself how many horizontal squares is between my pivot and my force line. Well, 0. So we get no torque from the second force. And then for the third force, we have a force of magnitude 1, and that's a horizontal force. So how many vertical squares away is F3 from my pivot point? Well, it's the whole square length 1, 2. So this actually also equals 2. So we see 1 and 3 are equal, and they beat 2. That's a 2-star. Oh yeah, I forgot. Energy conservation, multiple steps, that's a 2-star. Differential equation was also a 2-star. A disk of rotational inertia about an axle aligned with the center of the disk. All right. Here's our very official, not messed up problem here, where we have a disk has rotational kinetic energy K. And then if an identical disk, which is not rotating, is dropped onto the rotating disk, what is the total kinetic energy after the collision? So this is a rotational collision, so we're going to be looking at angular momentum. So we know that we can just conserve angular momentum to say our initial angular momentum is equal to our final angular momentum. So I0 omega 0 is equal to I final times omega final. And we weren't given any specific values here, but what we do know is that we're dropping an identical disk. So my system is really just 2 disks worth of inertia now. So I have doubled the rotational inertia of my system. So to compensate the angular velocity, it must be halved. And now we can just plug into the expression for rotational kinetic energy. And there's actually 2 competing effects. So yes, our rotational inertia doubled, but our rotational velocity got 1 halved, and that gets squared. So we get 2 times a fourth. So my new K is actually just 1/2 of the original. So the slowdown, if it was just a slowdown, we get a quarter, but there's that extra little boost from the mass. So I thought this was 2-star. There's a really simple way to do this if you recognize that angular momentum is constant. There's a relationship that I rarely use. Others really like it. You could say that K is equal to L squared over 2I. And you can see that here the angular momentum is constant, but the mass of the rotational inertia of the system got doubled. So you could just as easily argue in sort of 2 lines that the kinetic energy halved if for some reason you have this formula in your brain. All right, block of mass M is attached to a spring with force constant K. It's displaced to distance A from its equilibrium position. What is the magnitude of the maximum acceleration from the block? Well, we know that the acceleration is equal to force divided by mass. That's just Newton's second law. So this means that our maximum acceleration is just going to be our maximum force divided by the mass of the block. So here we have force from a spring is equal to K times delta X, an absolute value, of course. So what is the maximum force on the spring, or force from the spring? Well, what's the max displacement? It's going to be its amplitude A, right? Because the spring force can vary from nothing if you're at equilibrium to its amplitude A would be Ka. Knowing the maximizer thing, I bumped this to 2. This is pretty borderline a 1, though. This is the maximum force on the block. The others are frequency nonsense or just messing with energy. All right, last few here. A block of mass m moves to the right along a frictionless horizontal surface towards a stationary block of mass 3m, which has an attached spring. Which of the following bar charts could represent the energy and momentum distribution when the spring reaches maximum compression? So what we have to remember here is there's going to be 2 conservations. Momentum has to be conserved and energy. So what does it mean for maximum compression to happen? Well, this must mean that the spring is not expanding or contracting relative to either block. And this is just a fact for this specific type of problem that's a bit odd to think about. But what's true at this point is that the velocity of the first block is equal to the velocity of the second block, which is equal to the velocity of their shared center of mass, which should make sense, right? Because the velocity of the center of mass can't change in a closed system. And if the block velocities are equal to each other at this moment, it means the spring is not getting squished or expanded relative to either block. So the main point here is that the velocity is actually not zero. This isn't your standard put all your energy in the spring bucket and none in the kinetic, because you actually can't do that or else momentum wouldn't be conserved. So we just need a valid bar chart that shows both energies exist and both momentums exist. And the only option that fits that is answer choice D. And even though velocity is the same, we see that the 3m has triple the momentum because it's moving at the same velocity but has triple the mass. So that makes D the answer choice there. I actually bumped this all the way to 3. This is such a tricky scenario to think about, because this is such a convincing answer. Now you realize it's inconsistent with you can't have momentum without kinetic energy. All right, planet X has mass m and radius r. A satellite of mass m begins at rest and altitude r above the surface of the planet. How much work is required to move the satellite from its current position to a location far away from planet X? So what we need to do here is sort of just think about the energy. So currently, we know that U is equal to negative GMM over R, because orbiting bodies are sort of in this energy debt. And what is R? Well, R is actually the distance from the center. So if I'm at an altitude of R, I'm at R plus another R, which makes 2R. So what this means is that my initial gravitational potential energy is negative 1/2 GMM over R. So that's my initial energy. Now my final energy, if I move the planet very, very far away, this is just asking what is that energy? Well, my final energy of the system, because we're doing this slowly, so there's no kinetic involved, my final energy would be negative GMM over R, but R is very far away, so that's infinity, which is equal to 0. So if we look at our energy at the end, we have 0 energy. So we're just asking how much energy is required to go from negative 1/2 GMM over R, meaning I'm half GMM over R in energy debt, to 0. Well, we just use the fact that the work done by external forces is just the change in energy of the system, which is just going to be 1/2 GMM over R. That's how much energy I had to put in to free this planet from debt. Because of the subtleties here, I bumped this up to 3 also. Anything with energy in the negative sign gets people. And the fact that there's this altitude idea. All right, now for a breather at the end here. A lightweight string is attached to a disk of mass m. The disk is then released from rest, and the string unwinds, causing the disk to rotate without slipping as it falls. Which of the following is true about the translational kinetic energy of the disk after falling a distance h? Is it mgh, or is it not mgh? Well, we know with energy conservation that there are 2 types of kinetic energy. So our equation looks like mgh equals 1/2 mv squared plus 1/2 I omega squared. So if this term right here is the translational kinetic energy, we know that our translational kinetic energy is going to be less than mgh, because there's also this rotation factor. So it's going to be less because the disk also has rotational kinetic energy. This was a pretty standard 1 star. The string does negative work on the disk as it falls. That doesn't really make sense because the string is causing the string is actually causing this rotation to speed up. It doesn't quite work out. All right. Consider 2 carts, cart A and cart B, which both begin at the origin. The velocity of each cart is plotted below. we want to figure out what is true about the motion of the two cars. So we're just doing a whole bunch of things here. So we have a VT graph. So we're comparing displacements. We're looking at meeting points. It's easier to kind of look at the meeting point idea. So this is definitely a bait answer to say that 2 is the meeting point. So they both begin at the origin. So again, remember what is the relationship between distance and speed. So we know that our displacement is the area under the VT graph. So if we looked at what happened at these various times that we're claiming they meet at, let's see if the areas match. So at t equals 2, this area is just clearly, this area, this triangle area at 2, which is cart B's displacement, is clearly less than cart A's displacement, because cart A absorbs even extra. So it's definitely not C. And they also claim one of the meeting points could be t equals 4, so we can check that one. So at t equals 4, the blue area would be just a 4 by 10. And then the purple area would be a 1/2 times 4 by 20. And oh look, both of those are the same thing. So it displaces 40 meters, and then the other card also displaces 40 meters. So we see the displacements do match at t equals 4. And the other two are just clearly false, because if they meet at 4, that means that B starts winning the displacement battle after t equals 4, and then B is false because the average speed of cart B on the whole interval would be 25 over 5. That doesn't work out. Level 2. All right, still hard. Yeah, still some hard stuff in here, but good review nonetheless. I thought this hit everything. We'll do free response next.